Everyone, I'm Danielle Aminov, a threat researcher at Wiz. I specialize in helping organizations map their external attack surface and defend against threats in the cloud.
And I'm Yaara Shriki. I'm also a threat researcher at Wiz, and I specialize in researching emerging threats in cloud environments.
Okay, so in our talk, Auths Gone Wild, we're going to show you how resources that thought to enforce authentication actually allows anyone access. And today, many organizations store their sensitive data within the cloud, whether it's in buckets, storage accounts, and databases, and they want the data to stay private. So in order to ensure that, they use scanning tools to externally scan their attack surface for misconfigurations and vulnerabilities. And when they don't scan their environment properly, then the misconfiguration that we're going to talk about today actually remains a silent risk within their environment, as the misconfigured assets look private at first glance, but actually are publicly exposed and potentially exposes sensitive data without organizations even knowing about it. So let's see an example.
Okay, so before we begin, I want to show you a quick example of how easily someone might set up, accidentally, a misconfigured SQL database server. So let's just say you've just started a new project and you set up an Azure SQL database server and you want it to remain private, right? So you configure a firewall rule so only you can access it and anyone from outside cannot access it. Then you've added an app service, and you want the app service to be able to access your database server. So you configure another firewall rule that allows access from the app service IP to your SQL database server. But then let's say you've added another app service maybe, and another Azure function, and you wanted a quick fix to make everything work and not do it manually every time. So you might see this configuration that allows you to just give access from any Azure service and resource to your own server. And you might enable it. And you think, okay, great, now everything will work as expected, right? Now all of the services that you have can access your SQL database server. But what you didn't know is that it's not only your services that can access the database server. It's any Azure service can now has access to your database server. That means even attackers on, for example, an Azure function in another environment can now access your server.
Okay, so let's see the agenda for the next 20 minutes. So we start with the background and why we even started the research in the first place. We're going to move to the scanning methodology and how we scan resources for the misconfiguration. We'll have some findings, some really cool findings for the 3 big CSPs. Also, we'll have a quick peek into the tool that we use so you will be able to reproduce the scan on your own. And finally, we'll have the takeaways and we'll give you some quick fixes you can ship today. So what kicked it all off? As part of our work, we came across a leaked secret that was used by an attacker, and we were also able to track the origin of the secret, which was an S3 bucket. So naturally, we accessed the bucket to see if we are able to download the secret again, and the bucket returned a 403 forbidden message indicating that we don't have enough permissions to access to it. So we decided to scan the bucket again, now while we were authenticated to our own AWS account, and the server response changed to 200OK, and we were able to both list and get objects from the bucket, including the secret that we said earlier. So we realized that this bucket was actually misconfigured to allow any AWS account to access to it, to do both list and get objects. And this misconfiguration actually denies anonymous access while allowing any AWS account access to it. And since anyone can register to AWS, meaning that also an anonymous user can access the bucket and see the sensitive data within it. And that just got us thinking, how many more buckets out there exposing sensitive data and are misconfigured in that way? So we started to investigate. But first, let's see how attackers and bug bounty hunters usually do bucket hacking. So this is really a quick one. They're first with enumerating bucket names, and after enumerating bucket names, once they have a list of buckets, they start scanning them for misconfigurations, which usually derived by the bucket ACL and bucket policy. We're not going to dive deeper into that, but I will say there are many Austin tools you can use to perform bucket enumeration. There's the Cloud Enum tool you can use company name to filter the results, and also the AWS I tool, which you can use account ID to filter the results. So assuming now you have a list of buckets, now what's next? How you scan them for the misconfiguration? But before we answer that question, we need to understand who are we. So there are two predefined groups that are used both in AWS and GCP in the same way. It might seem obvious the differences between these two, but it also got us confused during this research, and I just want to make that clear. So all users are actually anonymous, any not authenticated entity out there trying to access your resources. And on the other hand, all authenticated users are any valid CSP authenticated principal. And most scanners actually use the all users predefined group. So just remember that. And now we're going to deep dive into the S3 scenario. So where this misconfiguration can hide in. So the first access model of S3 are bucket policies. This is in a JSON. It's written in a JSON format. It has multiple properties you can set up for how to define access to your bucket. So as you can see here, the principal is AWS asterisk, which is actually the all authenticated users predefined group. You also have actions and the resource that you can perform the actions on. And also, I will say that bucket policies also supports explicit denies, cross-account ARNs, and versioning. On the other hand, you have an older version of access model to S3, which is ACLs, also written in a JSON format, but this time you have a bit of different naming conventions. So here, instead of the principal, you have the URI, but here again, it's the authenticated users predefined group. And the permissions here is read, but effectively it also means listing a bucket, but also getting objects from it. So these two policies actually say pretty much the same and are leading to the misconfiguration. But how it happens? So first of all, of course, human error. And I do want to say a few words about that, even though it is pretty much obvious. But if you think about it, as a developer, you've launched the bucket and you want to make sure that the data is private. So you perform two tests. You start with anonymous scanning your bucket to see if it gets blocked, and it gets blocked. You receive 403 message forbidden, and that's fine. That works as expected. And then you move to the second test and try to access it while authenticated, and you use your own AWS account. And the response really was 200 OK, also as expected. So you perform the test, everything looks fine, but since you didn't use any foreign AWS account, so you missed that misconfiguration because you didn't scan properly the bucket. So yeah, that was the human error. All the other three are also pretty straightforward. So, of course, the copy-paste culture, you can see the Stack Overflow answer here with a command that leads to the misconfiguration. And also, even if you ask AI, it also can give you a misconfigured command. There are Terraform modules and all templates that also use misconfigurations, so you should be aware of that. And last but not least, also one-click wizards, but also overwhelming wizards. You just want something to work, you want the bucket to be public to you, and you accidentally click something, and now the bucket is misconfigured. And now we'll move to the scanning methodology. So we have a list of buckets, and we want to scan them and see if they are misconfigured. So we're starting with an unauthenticated scan as anonymous, and we're going to grab all the buckets that retrieve 403 forbidden message, so we can perform now an authenticated scan and see if the result has changed. So after scanning them while authenticated to our own AWS account, then the ones that change their response status code, we can say that they are potentially misconfigured. And why I say potentially? Because some of them were configured in that way because this was the first intention of the developer. I don't see why. But yeah, if you can track some sensitive information, secrets, and stuff like that, then I can say that, confidently say that this is a misconfiguration here. So after we scan, I do want to make a disclaimer, we didn't scan all the buckets on the internet, there are probably hundreds of millions of them, but we do usually perform scans on our customers' buckets. So we took a sample of it, about 60,000 buckets. So this is the 100% on the left. And then we start scanning them according to the methodology. So we start with the anonymous scan, which gives us 96% that seem private as they returned 4 or 3 message. And then we move next to the authenticated scan, which then we discovered that 99% of them were actually private, but 1 were effectively public, meaning that the response has changed and we were able to list and get objects from it. And the most important or maybe interesting thing that we discovered after analyzing the results, the majority of the effectively public were misconfigured and exposed sensitive data, such as API keys of secrets, PII such as health records, and also bank account numbers and credit cards. Really lots of cool stuff. And this is what we can show you. So you can see we were able to track Slack user tokens and also a bucket full of lots of SSH private keys that we were able also to download. Well, that was the S3 bucket scenario, and I will move the mic again to Yaara for the next one.
Thanks. So you might think now, okay, this is kind of a weird convention in AWS policies. But actually, it also happens in GCP. So we'll see now how it works here in Google Cloud Storage. So similar to AWS, we have here again the all users, which in the same way means any anonymous user or entity can access the bucket contents. And all authenticated users, again, mean just any GCP authenticated user or with a Google account. So if any of them tries to access your bucket, they can just read the content, right? So let's see how it works. Let's say we have a bucket. We know that it has the policy of the all authenticated users. How does it look like? When we first try to access it, being just from our local computer, we try to access, we get access denied. Okay, expected. Then we try to access it again, being authenticated just to any GCP environment. And now we see that we can actually read the contents of the bucket. So we can list all of the file names and actually read the content. So if you have confidential data in your bucket and it has the all authenticated users policy, then any authenticated users can read this data. Okay, cool. So how can you check yourself if your own buckets have this policy? There are a couple of ways to do this. First, you can just use the gsutil and list all of the policy names on your bucket. And if you see down there either the all authenticated users or all users policy, that means any user or an authenticated user can read your bucket. Cool, but that's not very scalable, and it may be hard to automate this process. So this is why we came up with Authent. Authent, it's an open source tool. We're releasing it today. I'll have the link for it and the QR code for the repo at the end of the presentation. Basically, it's a tool that you can scan automatically for all of the buckets that you have, either GCP or AWS, and see for yourself if any of them is misconfigured with the all authenticated users policy. So let's see a quick demo of how it works. So here we have a GCP bucket name, and we want to test it. So essentially, we're going according to the methodology. We're doing 2 scans, one unauthenticated and one authenticated scans. And we're going to look at the status code results. And if we see that the first unauthenticated scan got us a 403 and the second one got a 200, okay, then that means that the bucket has this policy of all authenticated users. Now let's go over the results. This is for the GCP bucket scanning that we did. We actually saw that 8% of GCP environment had this misconfiguration of all authenticated users. So we don't know if it's by design or not, but okay. But more than that, 36% of those buckets had actually stored sensitive data. So we found out credit card numbers, social security numbers, and bank account. And that's probably not desired by the developers. Now you might ask yourself, okay, we talked about AWS and GCP. What about Azure Blob Storage? The quick answer is that they're not vulnerable to this misconfiguration by design. So good job, Azure, in this case. But we found out another way that they do expose this misconfiguration. So in Azure SQL database, if we go back to the example in the beginning, you remember that we have this configuration where someone might allow any Azure service or resource to access resources, your own server, right? Your own database server. And what happens behind the scene is that it adds a firewall rule that makes any Azure instance, like an Azure VM, Azure function, being able to access your own Azure database server. And that, again, means anyone. So let's see a quick demo of how you can check it yourself. Here we just use the SQL CMD, and we are doing two scans, one from a local machine and the other from an Azure VM instance. And first we're scanning the same SQL database server, and we see an error code that says the client IP address is not allowed to access the server. That means we can read the property. Now, in the second scan from an Azure VM, we still get an error message, but this time it's login failed for the users. So although we still have an error message, it's different. It means that the attack surface has just grown larger, right? Because now an attacker who has access to this database server from outside can either brute force the credentials or try to use valid credentials and see all of the data in the SQL database server. So that's not wanted by the developers again. So going over the results for Azure. As expected, most of the servers that we checked were actually private. But then 2% were public. Maybe that's desired. But the surprising finding that we saw was that 10% of the servers had enabled the feature of the Azure services only. So that means that they might have thought that these servers are private if they use like traditional scanners, but actually they were just public servers. So we see that this problem is much larger than just database servers and buckets. It can happen in other resources or services as well. We didn't have the time to check, but we're sure that it might happen in other CSPs as well, other than the big three. And it's worth checking out for future research, and we're sure that there will be more issues like this one.
Okay, so now we have our takeaways. So we really wanted to give you sort of a framework for this misconfiguration coverage. And we go from tactical to strategic, but also from the easier actions to the more robust. So we'll start with the discovery. We'll map, you should map all the resources in your environment, and you should scan them anonymously, but also while authenticated, but also from multiple CSPs, so you won't miss any types of misconfigurations like this. Then you move to the detection part, so continuously analyze your policies and ACLs, so you should be able to see these misconfigurations in real time. And finally, the prevention part, so shift left least privilege by blocking risky configuration in a CI/CD pipeline, so these misconfigurations won't even deploy to production environment. So that was very quick, but
thanks for listening, and here's the QR code. You have the QR code for our tool, open source tool, and we'll be taking questions outside.